In this lecture, we shall discuss about heat engines and in particular the Carnot engine. A heat engine, or more simply an engine, is a device that extracts energy from its environment in the form of heat and does useful work. At the heart of every engine is a working substance. In a steam engine, the working substance is water in both its vapor and its liquid form. In an automobile engine, the working substance is a gasoline and air mixture. If an engine is to do work on a sustained basis, the working substance must operate in a cycle. That is, the working substance must pass through a closed series of thermodynamic processes called strokes, returning again and again to each state in its cycle. Let us see what the laws of thermodynamics can tell us about the operation of engines. We discuss now the Carnot engine. We have seen that we can learn much about real gases by analyzing an ideal gas which obeys the simple law PV equal to nRT. We know that here P is the pressure, V is volume, T is temperature, N is the number of moles in the substance, and R is the gas constant. Although an ideal gas does not exist, any real gas approaches ideal behavior if its density is low enough. Similarly, we can study real engines by analyzing the behavior of an ideal engine. We define an ideal engine in this way. In an ideal engine, all processes are reversible. And no wasteful energy transfers occur due to say friction and turbulence. We shall focus on a particular ideal engine called a Carnot engine after the French scientist and engineer Sadi Carnot, who first proposed the engine's concept in 1824. This ideal engine turns out to be the best in principle at using energy as heat to do useful work. Surprisingly, Carnot was able to analyze the performance of this engine before the first law of thermodynamics and the concept of entropy had been discovered. So the Carnot engine is an ideal engine. Okay, let us now discuss in detail the Carnot engine. To do this, we draw a figure. Uh, we have drawn um, the elements of a Carnot engine. The two black arrowheads, you see the arrowheads. The two black arrowheads on the central loop suggest that working substance operating in a cycle as if on a PV plot. Energy QH is transferred as heat from the high temperature reservoir at temperature TH to the working substance. Energy QL is transferred as heat from the working substance to the low temperature reservoir at temperature TL. Work W is done by the engine, actually by the working substance, on something in the environment. Now you see this in this figure. This is a Carnot engine. During each cycle of the engine, the working substance absorbs energy QH as heat from a thermal reservoir as I mentioned at constant temperature TH, and discharges energy QL as heat to a second thermal reservoir at constant lower temperature TL. If we draw the PV diagram of this Carnot engine, then it will be easier for us to discuss the working principle of the engine. Um, if we draw this here, this is a figure 1. And this is the PV diagram. And This AB is an isotherm at temperature TH, and this one another isotherm at temperature TL, this CD. This is A, this is B. Again we draw the same figure, but showing the heat QL that is being delivered from the working substance to the low temperature reservoir. So this is the isotherm TH, and this is the isotherm TL, and the work is W here. This figure 2, the earlier figure is 1, this is figure 2. This figure shows a PV plot of the Carnot cycle, the cycle followed by the working substance. As indicated by the arrows, the cycle is traversed in the clockwise direction. Imagine the working substance to be a gas confined to an insulating cylinder with a weighted movable piston. The cylinder may be placed at will on either of the two thermal reservoirs as shown in figure 1 here. In this figure, or on an insulating slab. The figure 2A shows that if we place the cylinder in contact with the high temperature reservoir at temperature TH, heat QH is transferred to the working substance from this reservoir as the gas undergoes an isothermal expansion from volume VA to volume VB. Similarly, with the working substance in contact with the low temperature reservoir at temperature TL, heat QL is transferred from the working substance to the low temperature reservoir as the gas undergoes an isothermal compression volume VC to volume VD. In the engine figure 1, this figure, we assume that heat transfers to or from the working substance can take place only during the isothermal processes AB and CD. Okay, so isothermal processes AB and CD. In the isothermal process AB, the temperature is fixed, which is TH, and in the isothermal process CD, the temperature is TL. Therefore, process BC and DA in this figure, which connect the two isotherms at temperatures TH and TL, must be reversible adiabatic processes. That is, there must be processes in which no energy is transferred as heat. To ensure this, during processes BC and DA, the cylinder is placed on an insulating slab as the volume of the working substance is changed. During the processes AB and BC of figure 2A, the working substance is expanding. So from A to B and B to C, you see the volume increases. So the working substance is expanding and thus doing positive work as it raises the weighted piston. The work is represented in this figure 2A by the area under the curve ABC. During the processes CD and DA, you see the CD and DA, the working substance is being compressed. You see the volume decreases. The working substance is being compressed. Which means that it is doing negative work on its environment, or equivalently that its environment is doing work on it as the loaded piston descends. This work is represented by the area under the curve CDA. The net work per cycle, which is represented by W in both figures 1 and figure 2, is the difference between these two areas and is a positive quantity equal to the area enclosed by cycle A, B, C, D. A. This work W is performed on some outside object such as a load to be lifted. Okay, now the equation where the entropy change delta S equal to SF minus Si is equal to initial state to final state, and this is dq by T. So this equation tells us that any energy transfer as heat must involve a change in entropy. To see this for a Carnot engine, we can plot the Carnot cycle on a temperature entropy diagram. Now we are going to draw it. This is temperature T and the entropy S. The lettered points A, B, C, D there corresponds to the lettered points in the PV diagram in the figure 2 here. The two horizontal lines in this figure 3 corresponds to the two isothermal processes of the cycle. Process AB is the isothermal expansion of the cycle, as the working substance reversibly absorbs energy QH as heat at constant temperature TH during the expansion. Its entropy increases. Similarly, during the isothermal compression, CD, the working substance reversibly loses energy QL as heat at constant temperature TL, and its entropy decreases. The two vertical lines in this figure 3 correspond to the two adiabatic processes of the Carnot cycle. Because no energy is transferred as heat during the two processes, the entropy of the working substance is constant during them. Now we can discuss the work. To calculate the net work done by a Carnot engine during a cycle, let us apply the equation for the first law of thermodynamics. And it was change in internal energy is equal to the uh, amount of heat energy minus the work done, W. That substance must return again and again to any arbitrary selected state in the cycle. Thus, if capital X represents any state property of the working substance, such as pressure, temperature, volume, internal energy, or entropy, we must have delta X equal to 0 for every cycle. It follows that delta E internal is equal to 0 for a complete cycle of the working substance. Is equal to 0 for a complete cycle of the working substance. Recalling that Q is the net heat transfer per cycle and W is the net work, we can write the first law of thermodynamics for the Carnot cycle as W equal to modulus of QH minus modulus of QL. Well, this is the work done. Okay, next we discuss about entropy changes. We have the total entropy change is delta SH plus delta SL, where delta SL is this and delta SL is where delta SH is positive because QH is added to the working substance as heat, and delta SL is negative because energy QL is removed from the working substance as heat. Because entropy is a state function, we must have delta S equal to 0. Therefore, we have this modulus of QH by TH is equal to, if we set this equal to 0, then we'll have this. We note that because TH is greater than TL, since TH is greater than TL, therefore QH is greater than QL. That is, more energy is extracted as heat from the high temperature reservoir than is delivered to the low temperature reservoir. Next, we shall derive an expression for the efficiency of a Carnot engine. The purpose of any engine is to transform as much of the extracted energy QH into work as possible. We measure its success in doing so by its thermal efficiency epsilon. This is known as thermal efficiency. And it is defined by this energy we get energy we pay for. And this is work done, and this is QH. This is efficiency any engine. Now for a Carnot engine, the efficiency is epsilon Carnot, and which is equal to QW, which is this divided by modulus of QH, and which is equal to 1 minus modulus of QL divided by modulus of QH. But we have found out that this relation, and from this relation QH by QL is QH by QL equal to TH by TL. So QL by QH equal to TL by TH, which can be written as 1 minus TL by TH. So you see the efficiency of the Carnot engine is 1 minus TL low temperature, and this is TH high temperature. Where the temperature TL and TH are in kelvins, because TL is since TL is less than TH, therefore efficiency is less than 1. That is, efficiency is less than 100%. It should be mentioned here that no real engine can have a thermal efficiency greater than that calculated from this equation. Inventors continually they are trying to improve engine efficiency by reducing the energy QL that is thrown away during each cycle. So the inventor's dream is to produce the perfect engine. Now I am going to draw it. Um, so the inventor's dream is to produce the perfect engine that I have shown here, in which QL is reduced to zero and QH is converted completely into work. Such an engine on an ocean liner, for example, could extract energy as heat from the water and use it to drive the propellers with no fuel cost. An automobile fitted with such an engine could extract energy as heat from the surrounding air and use it to drive the car, again with no fuel cost. Alas, a perfect engine is only a dream. It is not possible to achieve 100% engine efficiency. That is, epsilon C equal to 1 is not possible. It is not possible. This is the uh, inventor's dream. So TL equal to 0 or TH equal to TH tends to infinity is impossible. Because if TL equal to 0 or TH equal to infinity, then in this equation epsilon C becomes 1. But this is not possible. Therefore, epsilon C cannot be equal to 1. It is impossible. Instead, experience gives the following alternative version of the second law of thermodynamics, which says that this is the alternative way of saying the second law of thermodynamics. Alternative version of the second law of thermodynamics, which says there are no perfect engines. No series of processes is possible whose sole result is the transfer of energy as heat from a thermal reservoir and the complete conversion of this energy to work. To summarize, the thermal efficiency given by this epsilon c equal to 1 minus TL by TH for the Carnot engine, this is for Carnot engine, real engines in which the processes that form the engine cycle are not reversible have lower efficiencies. If our car were powered by a Carnot engine, it would have an efficiency of about 55%. Its actual efficiency is probably about 25%. A nuclear power plant, taken in its entirety, is an engine. It extracts energy as heat from a reactor core, does work by means of a turbine, and discharges energy as heat to a nearby river. If the power plant operated as a Carnot engine, its efficiency would be about 40%. Its actual efficiency is about 30%. In designing engines of any type, there is simply no way to beat the efficiency limitation imposed by the equation the efficiency of the Carnot engine. Okay, this is the end of this lecture.